Hello everyone, so it's a pleasure to present you Tam N'guyen. So he's working about water resources and water quality with numerical modeling with a physical base and as well with machine learning. And he's from UFZ.
Yeah, so thanks for the introduction and thanks Owen for having me here today. So in this talk, can you hear me? Maybe. Yeah. Okay. In this talk, I will talk about the age of stream flow and how can we make use of this information to understand the movement of water and transport of nutrients from the catchment to the stream. So as I know, many of you are expert in this field, so if I say something wrong, please correct me and I'm happy to learn more. So, and in a more scientific wording, so the title of my presentation is about transit time and how to make use of this to characterize rapid subsurface flow and slow groundwater flow that shapes stream water quality and quantity. So I have mentioned different terms, for example, water age and transit time, but what exactly do they mean? So let's start with some very basic definitions. So here we have a catchment, a figure representing a catchment with water of different ages. And let's assume that there's a rainfall event and now we start tracking a single water particle. For example, when the time it starts infiltrating into the catchment, we start defining its age. Now it has an age of 0. So after the first day, it moved to this location and has an age of 1 and so on. And after the third day, it exits the catchment and has an age of 3. So the transit time in this case, 3, is the time when water exits the catchment. When the water is still inside the catchment, we say this is a resident time. And in a similar way, we can also define the transit time, for example, for evapotranspiration, when the water exceeds the catchment through evapotranspiration. But let's focus in this case the transit time of discharge. So this is a general definition term for the transit time of any hydrologic system. And on a specific day, stream flow consists of multiple water particles of different ages. And then if we start counting the number of water particles in the stream and its age, and then we can make a histogram plot like this. And if the age discretization is small enough, this exactly represents the transit time distribution. Yeah, so we are talking about the transit time, but how to estimate the transit time? So there are several approaches. For example, the simple approach is the water balance approach. So in this approach, we assume that the system is in a steady state. In other words, we assume that inflow equals to outflow. So in this case, we cannot only estimate the mean transit time of the hydrologic system. For example, using this approach, Springer et al. Were able to estimate the transit time, mean transit time for different hydrologic systems at a global scale. For example, the transit time in the mean transit time in the unsaturated zone could be a year or more, or in surface water could be days to several years, and in the groundwater could be several decades. So stream flow consists of water from the unsaturated zone and also from the groundwater. So in a very rough estimation, we can say the mean transit time of stream flow could be several days to several decades, just very rough estimation. But this is not the mean transit time is not so informative. For example, when contaminants happen and we want to know when the first water particle appears in the stream and when the last contaminants move out of the catchment. So in this case, we can use tracer. So what is tracer? Tracer is any substance or physical properties of water that can be used to infer the movement of water within the hydrologic system. Yeah, thanks. So, tracer could be classified based on, for example, we could have natural tracer in rainfall, for example, stable isotope of hydrogen and oxygen, or could be deliberately introduced into the catchment, such as dyes. And tracer can be classified based on their reactivity level. For example, tracer that has very low level of reactivity, we call conservative tracer, for example, tritium and oxygen isotope, oxygen 18, for example, and or could be highly reactive, for example, nitrate. And the use of tracer to infer the transit time also depends on the spatial and temporal scale of interest. Yeah, the ideal tracer should be easy to quantify in the inflow and outflow, and the result from tracer data should be combined with kind of model to infer the transit time, which I will introduce later. And we can use also like physically based model to estimate the transit time. For example, in this study, my senior colleague, he constructed a hydrogeology model for the Sheffield catchment within the Tereno observation network. And here they calibrated the model for stream flow, and then they can conducted some numerical tracer experiment, and from that they can estimate the transit time of stream flow at the catchment outlet. For example, here it could vary from several days to almost a year. So the approach that I'm using now is the storage selection function, so-called the SAS function. So the underlying idea of the SAS function is that is to describe how catchment selectively remove water in storage of different age for discharge. So here we have a very nice graphical representation from Benedin and his colleague. So showing the catchment with water of different ages, and then if we make a histogram plot of water in the catchment with different ages, we will see like this. And then we could convert to the cumulative distribution, showing how much water in storage with an age age smaller than a certain threshold. And the next step in this approach is to assume the functional form of the SAS function, and then from that we can derive the transit time distribution of discharge, for example, in a cumulative form like this, or in this form showing how much water in discharge with certain age. And of course, we cannot assume any random SAS function. So in this sense, the tracer data came to play a role. And we should, the SAS function should be estimated in the way that the tracer concentration signal derived using the transit time distribution here should match with the observed data. So in the mathematical form, this concept could be expressed like this. Normally, so we have the water balance equation or the mass balance equation, but here we have the water and age balance equation. For example, here, showing the changes of water and its age in storage with time is due to the inflow, for example, precipitation, and outflows, for example, stream flow and evapotranspiration, and also the aging of water itself. And this is the SAS function. Once we assume the functional form of the SAS function, we can derive the transit time distribution of discharge. And based on the tracer signal in input and the transit time of distribution discharge in here, we can derive the tracer concentration in outflow. And we use this approach to estimate the transit time in the Selker catchment also within the Tereno observation network. And we assume different functional form of the SAS function. For example, here we use the power law distribution function or the beta distribution function. So using both functions, we can derive the tracer signal in the outflow, which are quite similar. But in terms of the transit time distribution, it shows that there's a clear differences in the estimated transit time. So there's a uncertainty in the estimated transit time due to the uncertainty in the unknown functional form of the SAS function. And in the other approach, we did not calibrate it with the tracer signal in outflow, but we calibrated the young water fraction estimated from the transit time distribution here with the young water fraction from other methods, for example, from the seasonal isotope signal in inflow and outflow. We assume this is observed young water fraction. And we apply this method to estimate the transit time for various catchments in the border. And we found that, for example, in this catchment with high young water fraction, so using the young water fraction estimated from other approach could significantly reduce the estimated transit time from the SAS function. But in other catchments with very low young water fraction, it does not have much. So far we have talked about the transit time and how to estimate it and the uncertainty, but we need to move on. So what is the use of transit time for understand hydrology and water quality? So let's go back to the previous study by Yang et al. Here. So they are able to derive the transit time for any modeling time step, and this is the cumulative distribution of the transit time. So let's have a close look at 2 days. A wet day, we have very short transit time or very fast flow, and a dry day where we have when we have very high transit time, long transit time. So here they can nicely link the transit time to the flow path characteristic of the catchment. For example, during the wet day, here is the cross section of this cross section. So here during the wet day, so the storage is high and the soil fully saturated. So this activates some short, shallow flow path. And when rainfall occurs, so water just follow this flow path and end up in the stream. That's why we have very fast transit time. But during the dry day, so the storage is low and the soil is dry, so water need to infiltrate through the soil and to the unsaturated zone and groundwater and then end up in stream. And in other words, like stream flow in the dry periods is mostly from the groundwater with a long flow path. So in this case, we have very long transit time. And here we use the SAS function to understanding the flow and solute transport in the headwater catchment in the Zell curve in here. And here we apply like the MHM SAS model to model nitrogen process within the soil zone and use the SAS function in the subsurface to quantify the nitrate transport. And here we use the different functional forms of the SAS function, allowing the SAS function to change its form, for example, preference for young water or preference for old water, depending on the ratio of the antecedent inflow and outflow. So mimicking what we understood from the physically based model. And we calibrated the model for stream flow at the catchment outlet here, and in-stream nitrate concentration also at the catchment outlet. And then we try to explain the in-stream nitrate concentration here using the transit time. For example, here showing the transit time, you can see the clear seasonal variability in the transit time of discharge in this catchment. For example, during high flow here, we have very short transit time, indicating that water from this period is mainly from the shallow flow path with fast transit time. Because the nitrate concentration in the soil is high, so we observe the high nitrate concentration in the outflow here. And during the dry period, so water is mainly from the groundwater with long transit time, so we have more time for denitrification. That's why we have very low nitrate concentration in this period. So, and one of the disadvantages of the SAS function is that this function, or the transit time, it just tells us that the temporal origin of water, but it does not tell us the spatial origin of water. For example, we have water in different ponds in the catchment, but it could end up in the stream with the same transit time. So knowing this limitation, we're trying to solve this by applying the similar model, but in a semi-distributed approach. For example, we apply the model for at a sub-basin level for the upper and the middle and the lower sub-basin in here. And then we try to explain the stream flow and nitrate concentration at the catchment outlet. Here we calibrated the model for stream flow at the three gorging station in here, and also for in-stream nitrate concentration at 3 gorging station. And as you can see here in the 2 upstream stations, we have a clear seasonal pattern in nitrate concentration. But for the lowland catchment in here at the catchment outlet, here we also have the seasonal patterns, but the minimum nitrate concentration is always above a certain level. And how can we explain this with a transit time? So as you can see in here, for the upper catchment, we have the also clear seasonal pattern in the transit time of discharge. And this explains for the seasonal patterns in the in-stream nitrate concentration from this catchment that's previously explained. And also we have the similar transit time for the middle Zelker and also similar nitrate export pattern in here. But for the lower Zelker in here, we found that the transit time is relatively stable and high. So in this catchment, there's very low denitrification. So despite having a long transit time, but because there are no condition for denitrification, so the nitrate export from this subcatchment is still relatively high and relatively stable. So that's why the integration of these nitrate export signal from each subcatchment create the seasonal nitrate pattern at the catchment outlet, but the minimum values is always above a certain level due to nitrate export from the lower catchment in here. And also using this approach, we can answer the question, where's the main contributor to stream flow and nitrate export at the catchment outlet. For example, in terms of stream flow, so the total flow in the upper two subcatchment here contributes more than 50% of stream flow at the catchment outlet. But in terms of nitrate export, the two upper subcatchments only contribute only minor amount during the low flow period. So during the low flow period, nitrate is mainly from the lower catchment. And in this paper, we want to use the transit time to understand the effect of multi-year drought in 2018 and 2019 on water and solute export from this catchment. For example, here you can see in 2018 and 2019 we have higher temperature and also lower precipitation compared to other years. And in terms of solute export, for example, nitrate, during the multi-year drought 2018 and 19, in here we see an increase in the seasonal patterns in the nitrate export. And here we can explain by using the transit time, for example. In the upper catchment in here, the transit time during the multi-year drought period, we have much higher transit time during the low flow and also much lower transit time during the high flow in here. Its cause is the increase in seasonal variability in nitrate export. This could be explained by the fact that for some soils, particularly those cracked during the long dry spell, and these cracks could act as preferential flow path during the wet day later, and causing the faster flow velocity or here shorter transit time. Or in some soil, for example, when heavy rainfall, after the dry period, when heavy rainfall occurs, it could lead to breakdown of soil aggregates and sealing the soil surface, so reducing the soil infiltration capacity and also increasing the transit time, or as you see here, the low value. But for the lower catchment in here, we see that the transit time during the multi-year drought is very high, so we expect that the effect of multi-year drought on stream water quality can be seen only many years later. So in conclusion, I would say that the transit time is quite powerful tool for understanding both water flow and solute transport, and there have been several papers calling for integration of the transit time into the water quality models. And the stored selection function that provide a coherent framework for incorporating the transit time into water quality model, as I showed previously, and also, but there are also considerable uncertainty in the estimated transit time, and we can have more data to constrain to reduce this uncertainty. For example, tracer data of in inflow and outflow. Yeah, and these are the references that I used. So thanks for your attention. Yeah.